Download this code from codegive.com, link in the description below. OK, let's dive into a comprehensive deep learning crash course for beginners. This guide will cover the fundamental concepts, provide practical code examples using TensorFlow, Keras API, and offer insights to help you get started on your deep learning journey. What is deep learning? Deep learning is a subfield of machine learning that utilizes artificial neural networks with multiple layers, hence deep, to learn complex patterns from large amounts of data. It's particularly powerful for tasks like image recognition, natural language processing, and speech recognition where traditional machine learning algorithms struggle. Key differences from traditional machine learning. Feature engineering. In traditional ML, you often need to manually engineer features, example identifying edges in an image. Deep learning automates feature extraction through its layered architecture. The network learns the relevant features directly from the data. Data requirements. Deep learning typically requires significantly more data than traditional ML to train effectively. The complex models have many parameters that need to be learned from the data. Computational resources. Training deep learning models can be computationally expensive, often requiring GPUs, graphics processing units, for faster training. Model complexity. Deep learning models are more complex than traditional ML models. 2. Core concepts, the building blocks. 1. Neural networks. A neural network is inspired by the structure of the human brain. It consists of interconnected nodes, neurons, organized in layers. Layers. Input layer. Receives the raw input data. The number of neurons in the input layer corresponds to the number of features in your data. Hidden layers. One or more layers between the input and output layers. These layers perform the complex feature extraction and transformation. The number of layers and neurons per layer are hyperparameters you need to tune. Output layer. Produces the final prediction. The number of neurons depends on the task. For example, for binary classification, example cat or dog, you might have one neuron with a sigmoid activation. For multi-class classification, example classifying different types of flowers, you might have multiple neurons with a softmax activation. Neurons, nodes. Each neuron receives inputs, applies a weighted sum, adds a bias, and then applies an activation function. Weighted sum. Each input is multiplied by a weight. The weights represent the importance of each input. Bias. A constant value added to the weighted sum. It allows the neuron to activate even when all inputs are 0. Activation function. A nonlinear function that introduces nonlinearity into the network. Without nonlinearity, the entire network would just be a linear transformation. Common activation functions include sigmoid. Outputs a value between 0 and 1. Used in binary classification problems. ReLU, rectified linear unit outputs the input if it's positive, otherwise outputs 0. A very popular choice for hidden layers. Tan, hyperbolic tangent outputs a value between -1 and 1. Softmax. Outputs a probability distribution over multiple classes. Used in multi-class classification problems. 2. Forward propagation. The process of passing the input data through the network, layer by layer, to obtain the prediction. Each neuron calculates its output based on its inputs, weights, biases, and activation function. 3. Loss function, cost function. Asterisk measures the difference between the predicted output and the actual output. Asterisk the goal of training is to minimize the loss function. Asterisk common loss functions. Asterisk mean squared error, MSE used for regression problems. Asterisk binary cross entropy asterisk used for binary classification problems. Asterisk categorical cross entropy asterisk used for multi-class classification problems. For backpropagation asterisk. Asterisk the process of calculating the gradients, derivatives, of the loss function with respect to the weights and biases in the network. Asterisk the gradients indicate how much each weight and bias contributes to the loss. Asterisk backpropagation uses the chain rule of calculus to calculate these gradients efficiently. 5. Optimization asterisk. Asterisk the process of updating the weights and biases to minimize the loss function. Asterisk gradient descent asterisk a common optimization algorithm that iteratively adjusts the weights and biases in the direction of the negative gradient. Asterisk learning rate asterisk a hyperparameter that controls the step size during optimization. A smaller learning rate may lead to slower convergence, while a larger learning rate may cause the optimization to overshoot the minimum. Asterisk other optimization algorithms asterisk atom, RMSprop, SGD with momentum, etc. Atom is often a good starting point. 6. Epochs, batch size, and iterations asterisk. Asterisk epoch asterisk 1 complete pass of the entire training dataset through the network. Asterisk batch size asterisk the number of training examples used in one iteration of the optimization algorithm. Asterisk iteration asterisk 1 update of the weights and biases based on a batch of training data. 3. Implementing a simple neural network with tensorflow/keras. Let's build a simple neural network to classify handwritten digits using the NIST dataset. Explanation of the code asterisk. 1. Import libraries asterisk import TensorFlow and keras, TensorFlow's high-level API, and matplotlib for plotting. 2. Load the NIST dataset asterisk. Asterisk keras.datasets.nist.load_data, loads the NIST dataset, which consists of 60,000 training images and 10,000 test images of handwritten digits, 0 to 9. Asterisk x_train, y_train, training data, images and labels. Asterisk x_test, y_test, test data, images and labels. 3. Data pre-processing asterisk. Asterisk scaling asterisk divide pixel values by 255.0 to normalize them to the range 0, 1. This helps the model train faster and more effectively. Asterisk flattening asterisk reshape the 2D images, 28x28 pixels, into 1D vectors, 784 elements. The dense layers expect a 1D input. Asterisk 1 hot encoding asterisk convert the labels, digits 0 to 9, into a 1 hot encoded format. For example, the digit 3 becomes 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. This is necessary for the categorical_cross entropy loss function. keras.utils.to_categorical, performs this conversion. 4. Build the model asterisk. Asterisk keras.sequential, creates a sequential model, layers are added in sequence. Asterisk input layer asterisk keras.layers.input, shape equals 784, specifies the input shape, 784 features. The input layer explicitly defines the shape of the expected input. Keras can sometimes infer the input shape, but it's good practice to define it explicitly. Asterisk hidden layer asterisk keras.layers.dense, 128, activation equals ReLU, adds a fully connected, dense, layer with 128 neurons and the ReLU activation function. Asterisk output layer asterisk keras.layers.dense, 10, activation equals softmax, adds the output layer with 10 neurons, 1 for each digit, and the softmax activation function. Softmax ensures that the output is a probability distribution, the probabilities of each digit sum to 1. 5. Compile the model asterisk. Asterisk model.compile, configures the learning process. Asterisk optimizer equals Atom, uses the Atom optimization algorithm, a good general purpose optimizer. Asterisk loss equals categorical underscore cross entropy, uses categorical cross entropy as the loss function, appropriate for multi-class classification with one-hot encoded labels. Asterisk metrics equals accuracy, tracks the accuracy during training. 6. Train the model asterisk. Asterisk model.fit, trains the model on the training data. Asterisk epochs equals 10, trains for 10 epochs, 10 complete passes through the training data. Asterisk batch underscore size equals 32, uses a batch size of 32, processes 32 training examples at a time. Asterisk validation underscore split equals 0.2, reserves 20% of the training data for validation. This allows you to monitor the model's performance on unseen data during training and detect overfitting. The validation underscore data argument could also be used to pass a separate validation set if you have one. Asterisk the history object returned by model.fit, contains information about the training process, such as the loss and accuracy at each epoch. This can be used for plotting learning curves. 7. Evaluate the model asterisk. Asterisk model.evaluate, evaluates the model on the test data. Asterisk loss, the loss on the test data. Asterisk accuracy, the accuracy on the test data. 8. Make predictions asterisk. Asterisk model.predict, makes predictions on the test data. It returns a number pi array of probabilities for each class, digit, for each test example. Asterisk np.argmax, predictions, axis equals 1, finds the index of the class with the highest probability for each example, i.e., the predicted digit. Asterisk the code then prints the predicted class and the actual class for the first 10 test examples. 9. Plotting training history asterisk. Asterisk the code plots the training and validation accuracy and loss over epochs. This helps you visualize how well the model is learning and whether it's overfitting. If the validation loss starts to increase while the training loss is still decreasing, it's a sign of overfitting. 4. Key concepts in action. Asterisk layers asterisk the code demonstrates the use of dense layers, fully connected layers. You can experiment with adding more hidden layers, changing the number of neurons per layer, or trying different activation functions. Asterisk activation functions asterisk the code uses ReLU and softmax. Experiment with sigmoid or tan to see how they affect performance. Asterisk loss function asterisk the code uses categorical underscore cross entropy. If you were doing binary classification, example classifying images as cat or not cat, you would use binary underscore cross entropy. For regression, use MSE, mean squared error. Asterisk optimization asterisk the code uses Atom. Experiment with other optimizers like SGD, stochastic gradient descent, or Reams-Prop. You can also adjust the learning rate. Asterisk epochs and batch size asterisk experiment with the number of epochs and the batch size to see how they affect training time and performance. Larger batch sizes can sometimes lead to faster training but may require more memory. More epochs can lead to better performance, but also a risk of overfitting. Asterisk validation asterisk the validation underscore split argument in model.fit is crucial for monitoring the model's generalization ability. Pay attention to the validation loss and accuracy to detect overfitting. Advanced topics, brief overview. Convolutional neural networks, CNNs excellent for image recognition. Use CONV2D layers to learn spatial features. Recurrent neural networks, RNNs well suited for sequential data like text and time series. Use LSTM or GRU layers. Regularization techniques to prevent overfitting, such as L1/L2 regularization and dropout. Transfer learning leveraging pre-trained models, example trained on ImageNet, and fine-tuning them for your specific task. This can save a lot of training time and improve performance, especially when you have limited data. Hyperparameter tuning optimizing the hyperparameters of your model, example learning rate, number of layers, number of neurons per layer. Techniques include grid search, random search, and Bayesian optimization. 6. Practical tips. Start small. Begin with simple models and gradually increase complexity. Visualize your data. Understanding your data is essential for building effective models. Monitor training. Track the loss and accuracy during training to identify problems. Use a GPU. Training deep learning models on a GPU can significantly speed up the process. Google Colab provides free access to GPUs. Read the documentation. The TensorFlow and keras documentation are excellent resources. Practice regularly. The best way to learn deep learning is by doing. 7. Further learning resources. TensorFlow tutorials. https://www.tensorflow.org/tutorials, https://www.tensorflow.org/tutorials. Keras documentation. https://keras.io/ https://keras.io. Deep Learning Specialization on Coursera, by Andrew Ng. A comprehensive introduction to deep learning. Fast.ai. Practical deep learning courses. Books. Deep Learning by Ian Goodfellow, Yoshua Bengio, and Aaron Corville. This detailed guide should give you a solid foundation in deep learning. Remember to experiment, practice, and explore the vast resources available online. Good luck.